Hello, testing. Hello. All right. Have you guys looked through the lecture notes for last week? Have you looked through? Have you already read it? No, not yet. Okay. How about the rest? Got read or not? Also, the tutorial. Look at it. At least the solution. So, another thing to say, MA1 is like a kindergarten. It's a pure maths kindergarten. So, what do you do in kindergarten? Sleep. I know you play with friends, but other than that, what's your work? What's your work? Like, what kind of homework you get? Very simple. Like how do you execute the task? First of all, filling the blank, right? No, I think that one is already advanced. Yeah. So you like repeat your A, repeat like 100 times like that, right? Yeah. So this is the same as MA1. You need to keep writing proof. You can just copy first. Like kindergarten, you don't know why you copy A, right? You just write A first. Keep writing A, keep writing B, or 大小, write 大小 100 times. Okay, until you know how to write, and then you will start to appreciate what is A, B, C, D, and then it forms the word, right? Cat, and so on. Okay, actually, kindergarten nowadays is getting harder. I saw them like study those vocabulary that is very, very hard. But they only know how to read, only know how to read, but maybe not the meaning itself. Because they learn the phonics. So they see a lot of weird word. Okay. Yeah, so please keep practicing. And this thing I cannot control you. You have to make your own effort, okay, to do those exercises. What I can do is I give feedback to you through assignment, whether you do it correct or not. I cannot check everyone's tutorial, right? Okay, not enough time. Hopefully, next time, if the class have some, how to say, have some changes like reform to the structure of the class, then we will get some tutor to help as well, not just me. Okay, tutor. And hopefully, there's one thing I want to push is not just Max Help Center. I want to push the student council, okay, to do maybe a study group or study workshop like that to help you guys understand other than the lectures time. For example, I think it's worth to do like Epsilon Delta workshop or something like that. Right? Okay, give you more chance. Okay, you can learn from your senior because they just freshly graduated from this course, so they will know. Okay, know better. What is your problem? What's your concern? Right? What's your confusion? Okay, they will answer you better. And maybe you think that your senior is better approach than the lecturer. Okay, because maybe in Asian teaching, you are like, 敬而远之. You know what's 敬而远之? I respect you, but I stand far from you. 敬而远之. Okay. So, yeah. So maybe this will help better if you have a senior helps. Of course, you can go to Max Help Center. Max Help Center is really under usage, so you should go. You know what is under usage mean? 简单，也就没有人用就是了。Okay, yeah, under usage 没有人去问。So please go. Okay, you can get help from them. Okay, they are the master students here. Okay. Right. Okay. There's some bookkeeping we have to do before we discuss about stuff today. I've updated some terminology inside my lecture notes. So, for example, we talk about partition is finer than delta. What does it mean by partition finer than delta? Finer. Finer means smaller, right? So what's the thing that's smaller? Okay. Anyone remember? What does the partition finer than delta means? Yeah, what is final here? So you have a partition, right? So partition of what? Partition of a maybe closed interval such that your first point is the left endpoint, the last point is your right endpoint. Okay, then you have a bunch of points in between left and right endpoint. Okay. For example, x s0, x1, x2, x3, x4 up to xn. Okay. And what does it mean by finer than delta means this partition? So what sort of length you can pick up from this partition here? You can't really control the length of the original interval, right? Because it's given. But what can you control there? So given an interval, how many kind of partition you can give? How many times? Yeah, how many? If I ask you to partition one interval, how many kind of partition you can give? Infinitely many, correct or not? Because you have infinitely many numbers in between, say, interval A and B, A, B, in between A, B. If you gave a partition, you can look at the sub-interval built up by, let's say, in this case here, we denote it T naught to Tn. So you can compute the length of Ti minus Ti minus 1. So meaning from the first partition point to the next partition point, how far is it? If all this distance, right, is less than delta, then we'll say that the partition is finer than delta. Okay. So, I mean, let me give you an example here. Say, let's say P equals to 0, 1, 2, 3, 4, which is a partition of 0, 4. So this partition here is finer than what? What number? It's finer than what? What is the delta you can choose here? What is 1 minus 0? What is 2 minus 1? What is 4 minus 2? Huh? Yeah. So what delta then? What delta you can choose here? 3, for example, right? Because all the length of the sub-interval is less than 3. Okay. Or you can choose delta to be, well, what 3 I wrote here, the set notation. Or you can pick delta to be 2.5 also. Correct or not? 2.5. Okay, as long as this delta is greater than 2, then you can pick it as your delta here. So we created this delta, right, is to define the Riemann sum. Okay, remember we do the Riemann sum. And the assignment for Riemann sum already out. The last assignment you do for this course. So you have like about 3 weeks to do it. Okay, so please arrange your time properly. Okay, and then try not to get extension for this assignment because this is last assignment and we try to get feedback on time to you also. Then everyone can do proper revision. Okay, so please keep this deadline in mind. And where's our final? Where's our final exam? Final. So it's the second week, huh? Last day, last time section. Wow. Okay. So you got plenty of time to do revision. So maybe we can try and arrange revision class. Okay, maybe, and we can even arrange 2 maybe. one in this study week, one is before your exam week. If you want.
Yeah, 1 week subject.
Which subject and which subject? Second last. Oh, okay, yeah. So we can make one revision there as well. And we also can make one during the study week. Yeah, we can make two. Okay. Yeah. I know that this course is pretty hard. So I'm willing to give extra class. Okay, if you are willing to learn. Okay, as long as you are willing to learn, I can help you as much as I can. Okay. Okay, so talking about this P finer than delta here, we didn't have how to say proper definition to talk about the maximum of this length here. So we define mesh size or norm of P to be the maximum of this length of interval. So you can see that to make sure that your P is finer than delta, you just need to make sure that this norm is less than delta. Correct or not? This is how you pick 3, right? Because you pick among 1, 1, 2. As long as your delta is greater than 2, then that's your desired delta here. Okay, so actually you are looking for the maximum of the length of subinterval here. Okay, in other words, we are looking for the norm less than delta. Okay, this will make things too easy to explain. Instead of we just talking about P is minor than delta. Okay, we just use norm of P is less than delta. Does it make sense? Just some terminology here. Okay or not? So why we prefer this terminology than this delta here? Because you can see that if I put this terminology here, this will become some mathematical symbol here. Again, some mathematical symbol here. So it's finer than got 3 words. But here, only have 3 symbols here. Does it make sense? Okay or not? So that's why we introduce this new definition or notation here. Does it make sense? Okay or not? Okay, so that's why you will see in some mathematical black box you see a lot of symbol. Why there's a lot of symbol there? That sometimes people say look at the mathematics 数学的黑板像看到天书这样。为什么看到天书呢？ Because behind every symbol there's a meaning. You see, if there's already so many symbols there, so you think how many paragraphs I need to fit in, okay, to talk about this many symbols. So that's why we use symbol because it summarizes the idea. For example, norm less than delta summarize the idea of finer than a partition finer than delta. So P is finer than delta got 5 words, but norm of P less than delta only got 3 symbols. So it reduced significantly. Does it make sense? Does it make sense? Okay. Okay, so that's why we tend to define new words, tend to define new notion because we want to encapsulate the all idea or notion. Okay. So far so good. Okay, understand the notation here because the norm will be used inside your assignment. Will be used inside your assignment. Does everyone get it? What is norm of P now? Yeah. Okay. Okay, good. Come back to talk about last week. Do some recalling of this example here. So we look at this linear function fx equal to x. Okay, how to draw the linear function is the y equal to x line here. And then we try to prove that f is integrable and then show that the Darboux integrable is b squared minus a squared over 2 for integral on the closed interval a to b. Okay, a to b. Right. To show f is integrable, what's the definition of f being integrable? Let's recall. What does it mean by a function to be the Darboux integrable? Yes, upper integral equals to lower integral. So how do we define upper integral and lower integral? Upper integral is what? Infimum or supremum? Huh? Infimum of all the upper sum. Okay. And then lower integral is the supremum of the supremum of the lower sum. Because when we do refinement, right? Think about refinement. When we do refinement of partition, the lower sum will increase, and then the upper sum will decrease. Okay. But we didn't use the definition to show it here. Instead, we use the theorem of integral analytically. What does it mean by that theorem? F is integrable if and only if for every epsilon there exists a partition such that UFP minus LFP is less than epsilon. Okay, they get really close. There is a partition exists for every epsilon such that the difference of UFP and LFP is really small. Okay, so remember this result. If you forgot, go back and look for the proof. How we prove it. The proof is not too hard. So the jobs here is to find an epsilon, to give you an epsilon and then find a partition such that UFP and LFP get really close. Okay, so what do we do is, it is quite similar to what you did in your Riemann sum, you know. What you did in your Riemann sum, you decide what is the length of your subinterval here. So I also decide my length of subinterval here. So I just simply split AB, the interval, into n subintervals. Okay. So meaning what? Meaning I take B minus A divided by n. Okay. Divide by n. And then this subinterval here, this length here will become my length of my subinterval. Okay, does it make sense? So for example here, in this picture here, let's say the leftmost is A, the rightmost is B. Okay, so what's the next point here? Okay, so the next point here is just A plus B minus A over n. Okay. And then can you guess what's the second point here? Hanwei, not Ethan. Hanwei. What's the next point in this partition? Yeah. Times 2. Okay. So you add 2 multiple of B minus A over n. Okay. And then so on. You can see that once you add up to n, okay, up to n, you get the last n point here. Does it make sense? Okay or not? So how should you imagine here? How should you imagine this kind of n? I found out the problem with the student, for example, first year, why they hate linear algebra so much. Because the first year I asked you to come in, I asked you to deal with n. What is n? Now, what is n here? Why I put n here? What does this n mean? This n can be what? Yes, n can be 1, 2, 3, 4, 5, 6, 7, n. Because we want this way of partition AB become a general process. For example, when n is 1, what does this mean? I just have 2 points. One is A, one is B. When n equals to 1, meaning the length you take is just B minus n. N equals to 2, what does this mean? You cut this interval into half. Okay? You cut it because B minus A over 2 is what? It's really the half length of B minus A. And then so on like that. Okay. So when you look at the problem of n, right, you have to really plug number into it. Okay, it's not just random n. you need to plug n equals to 1, 2, 3, 4, 5, 6, so on. Okay or not? Okay, whenever you see problem of n, remember, plug number into it. You will see it. Okay, you will see it. So you need to see it from small number first. So what does it mean by n equals to 1? What does it mean by n equals to 2, 3, 4, 5, 6? And then you will see the pattern. And then you will join the word of problem of n. Then you will understand why we phrase it as n. Okay. Okay. So why do I do this? So let's compute what is UFPN and LFPN here. Okay, UFPN and LFPN here. So to compute UFPN and LFPN, what do you need to compute? You already get the length of your subinterval. What you left with is the capital MI and the little mi. What's capital MI? Is the supremum of your function. What is your little mi? Is your infimum of your function. So among this subinterval, you need to figure out what is your supremum and infimum. Okay. In this case here, this function is easy to see. Why is it easy to see here? This function is increasing. Okay, you can use the method we have proven for derivative chapter to check that this is increasing. So if this function is increasing, okay, I give a subinterval. Where is the infimum? Where is the supremum? Within a subinterval. And where? What does f increasing means? Fx less than fy if what? If x less than y. So where is the largest fx? Where is the lowest fx? Sorry? Sure. So fb is what? Largest. Fa is smallest. So this is for AB. But how about if I shrink this interval to smaller interval? Call it, let's say, what do we call it here? Tk minus 1 and tk. So where is the largest point? Where is the smallest point? ftk is largest and ftk minus 1 is the infimum. Okay, so this is what we computed here. Okay. And what is tk? What is tk minus 1? Depend on how we define the partition. Okay or not? Make sense here? So far, so good. Okay. So what can you see here, from this two here? The way we pick our partition, these two numbers seems like behave quite well. What do I mean by behave quite well? What's the difference between them? The difference is only by a b minus a over n actually. Okay. Actually behave quite well. Okay. The difference between them is just this b minus a over n. Does it make sense? Okay. So you got the supremum, infimum of f already. Then you start to plug in into LFPN here. And I have a better calculation here. Finally, last time we was like going through the jungle and lost into the jungle last week. So we have a better calculation here, so that you can check. And finally, you get to this easy form here. Okay, b minus a plus b plus a over 2 minus b minus a square over 2n. Okay, this is for LFP. UFP is what? UFP is this one. Is it correct or not? Yeah, correct. So UFP is this. What is this? So instead of minus, we have a plus here. Okay, you can check the calculation. Okay. So how to do the epsilon thingy? So let epsilon greater than 0. How do we pick the n we need? We need to pick this n greater than this epsilon business here. You should now recall why I want to choose this kind of n. Okay, because when we want to compute the difference of UFP and LFP, we'll get to some form like this: b minus a squared over 2n. over n. And then we want to make this less than epsilon. Okay, so that's why we pick n greater than b minus a squared over epsilon. So please recall the epsilon argument that we learned before. Okay, so that's why we spend quite a long time, okay, dealing with this epsilon n business, because we're going to show something more important here, which is the integrability. Does it make sense? Can everyone follow? Okay. Yeah. So now what we do is for every epsilon, we found a p epsilon, which is this pn here. Okay, this pn here. Such that it works. So this shows that f is integrable. Okay, but we have do some magic last time. What magic we do last time? Somehow when we compute this L integral of f, we just compute the limit of this guy here. Okay, we do some magic here. I didn't really justify last time. But how you find UF and LFP, UF and LF, the upper integral and lower integral? You need to consider all partition. But here we only consider one type of partition. Is it enough or not? I will only consider one type of partition, which is this uniformly spread subinterval. Okay, is it enough? Is it enough? What do you think? Is it enough or not? Yes. At least from this result, yes, because it computed what we want, right? Correct or not? So to be precise, right? I have put in this theorem here. Okay, which is this common limit criteria here. So this theorem will help you to compute your Riemann integral. The Darboux integral. Okay. So first statement is if f is integrable, then there exists a sequence Pn such that limit of L Fpn is just your integral. But this doesn't apply to our case. Apply or not? Actually apply, because we already proven it is integrable. But how do we know that the Pn we built is the Pn in this question? Okay, so we don't quite know. But the second statement come to help here. Let's say you have a sequence of Pn such that limit of LFPn equals to L UPn. If these two limit equal, then that limit is exactly your integral. Okay, so this is what we use in the example above here. So let's check whether it is true or not. So, I mean, in this case here, let me check. In this case here, limit of Fpn is what? Okay, let us check here. Limit of n to infinity of LFPn is equals to this guy here. Limit of this guy. Is here. Is this guy here. Should we? Okay, let's remove this guy. Yeah, let me remove all these. Give us some space. Okay, so let's check whether this is true or not. Yeah. So if you take this these two terms here goes to n goes to infinity, what do you get? The second term here should disappear. Okay, so what you left with is really b squared minus n squared over 2. Does it make sense? Okay or not? How about UFP here? How about UFP? Remember what's the difference between LFP and UFP here? They are just the same, differ by a sign. Where's the sign differ here? The sign differ here happens at the second term. Okay, so what's the limit of this guy? So the second term also goes to 0. Okay, so what you left is the same, b squared minus n squared. So they are equal. Okay, no? Does it make sense? So if as long as you found a Pn such that the limit of LFPn equals to UFPn, then this is the Brooks integral. Okay, no? As long as you found one. You no need to check for or LFPN. Sorry, or LFPN or UFP. Okay, if you have one sequence that reach the same limit, then you are good. Okay, no? So the proof is not too hard. I included in the lecture notes already. Okay, so the proof is not too hard. Okay, the proof is not too hard. Where the proof actually uses some nice property that we have learned, like squeeze theorem for sequence, for example. Okay or not? Okay, using squeeze theorem. Okay, you can prove it. So the idea was you can use your LFPN and UFPN to bound your upper integral and lower integral. And then since these two have the same limit, then LF must equals to UF. And then it also equals to the limit of UFPN and LFPN. Okay. So actually this is the main part we have used squeeze theorem. So why we can reduce to checking all partition to just a sequence of partition actually is due to this property of LF and UF and also squeeze theorem. Okay, you can look at this proof. Actually, it's not too hard. Okay, just that you need to spell out the detail here. Everyone see or not? This inequality. This is the main thing we need to show that the limit of LFPN and UFPN is equals to the UF and LF, which is the Wood integral. Make sense? Okay, no? Squeezed by two things that have the same limit. Make sense? Okay, squeeze theorem. In the end, you still come back to squeeze theorem. Any questions so far? Any question? Is everyone okay with finding the Brooks integral now? Okay, as long as you can find a sequence such that UFPN and LFPN sequence of partitions such that LFPN and UFPN have the same limit, then you can find the Brooks integral. Okay, that's what. Okay. Any questions so far? Before we jump into what we haven't done finished last week. Any questions so far? Any question? No. No one? Okay. So please, once you understand what I say, please go back and read the lecture notes. Okay. Please go back and practice the lecture notes. Very good. I read a very good sentence wrote by Sun when he introduced the books. He was doing the books integral. So this guy is called Gaston the books. Gaston the books. He said that the books in France. Is he in France? France, right? Okay. Yeah, he was teaching maths in France. So he said that how he teach. He teach by mixing intuition and formalism together. Correct? No? This is what you wrote. Okay, so this is also what I was trying to do. Okay, we want to mix intuition and formalism together. Okay, so when I explain stuff, right, sometimes I explain it quite casually. You might think that it's quite casually. Actually, there's a whole bunch of formalism machinery behind it. So this formalism machinery is what I included in my lecture notes. So you cannot just listen to what I say in class. Okay, you also at the same time you need to read what I wrote in the lecture notes. So these two have to match together. Does it make sense? Okay, you cannot just listen to half. Half is no use. If you don't listen to me, you just read lecture notes, you will feel very hard, very dry. Okay. So I describe my lecture notes as very dry. What is dry? It's like in Chinese, people say 干货. 干货, you know what is 干货? What is 干货, Tony? OK，可以。这个是抖音这么介绍的吗？干货怎么介绍？来，抖音达人。哦，干货什么？使用的技巧绝对不水啊！我是绝对不水哦，一点都不水，是满满的干货。OK，使用的技巧也有这层意思有比较贬义的意思吗？哦，没有没，真的吗？不是说很难消化吗？干货蛮难消化，对不对啊？不是很好，所以确实不好消化，所以你要用我的润滑剂。不是我的润滑剂啊，你就要听我讲哦，听我说怎么解释它，这就是润滑剂。OK，放在干货上面，它就不干，好吗？可以吗？别水货不要太水啊，OK，不要太水，吸不好啊，拉稀不好。OK，好，right. So about this integrability we have done. So we come to this property of integrability. Actually, these proof are quite, how to say, straightforward. Maybe it's long, but it's kind of straightforward. In first side, let's choose among these six, maybe six of them. Which one do you think you want to see a proof on? Among six of this. So among six of this, which one do you think you want to see a proof on? Just simply decide one. What do you think? Then we can go detail to one of them, maybe. Two. Okay, two. Good. Actually, two is a very good choice, you know. Why two is a good choice? Two is the most tedious one. Why two is quite tedious? Look at this sentence here. If a less than c less than b, then the integral of fx from ab is equals to integral of ac plus cb. So what's the condition you have here? What's the assumption you have here? You only know that f is integrable at ab. So the first question to ask is, why can you write down integral from a to c and c to b? Why? To be able to do this, you need to argue that f is integrable on a to c, and also f is integrable from c to b, so that these two notation exist. Correct? No? Integrable only this notation, this number defined. And then next thing you need to show is actually the integral of a to b is equals to integral from a to c plus c to b. So you need to show that these two side number is the same. How to show that two number is the same? Their difference is less than, is equal to 0, or in other words, the difference is less than, the absolute difference is less than, or epsilon greater than 0. Okay? No. So this is the thing you need to do. Okay? It is always easy to say than to be done. Say is very easy, but you need to do it. Okay, so how do we do it? Let's see how do we do it here. So we have two jobs here. First job is to show that f is integrable from a to c and c to b. Second job is to show that the two side is the same number here. Okay, so there are two jobs going on here. Let's see how to do the first job. How to do any idea to do the first job? How to show the first job? How to show the first job here? C is AB, sure. Good. Let me think. So, a bit dangerous here. Do we assume F and G continuous or no? No. Correct. No. Integrable doesn't imply continuity, right? Remember, we can integrate a discontinuous function. Okay. Okay, you can't quite use continuity there. So what can you do now? Let's try discuss this question and then we can take a break later and then we can continue. Okay, so let's finish up this proof. So if we cannot use continuity, what else we can do? Sure, partition, good. Sure, we can, let's say we partition AB into ACB, for example, like that. Sure, can. Do more refinement, sure. Okay, do more refinement. So meaning you take refinement of the partition AB that contains C. Okay, and then what? Sorry? Uh-huh. Okay, so let me see. So should we write down what you say? This first proof. Show that. So first step. So step one. Show that F is integrable on AC and CB. A, B, and CB. So how do you fix? So what do you do? So you fix one partition. AB, sorry, AB. E that in C. Okay. That contains C. But what are you trying to do with this partition? What are you trying to do? You want to show that what? You want to show that it is integrable for CB and integrable on AC, right? So maybe we just pick one of them to do first. Let's say we want to show that it is integrable on AC. What do we need to show? How to show a function is integrable? Using the theorem of integral analytically. For every epsilon, what do you need to do? There exists a P epsilon such that U of F, let's say F restricted to AC of P epsilon minus L of F restricted to AC of P epsilon is less than epsilon. Okay or not? Does it make sense? Okay, make sense or not? This is one of the way to show the integral is integrable, other than showing UF equals to LF. Okay, you need to do this epsilon thing. For every epsilon, there is a p, such that UF p epsilon minus LF p epsilon is less than epsilon. So how to find this p then? So your job is to find out this p. How to find out this p here? How to find out this p? And then show that something is less than epsilon. But what's your assumption? What's your assumption? Assumption, what do you have? Huh? F to A to B is integrable. Okay, A to B is integrable. So there already exists, let's say, P prime epsilon of AB such that U of F, let's say, P prime epsilon minus L F of P prime epsilon is less than epsilon here. Okay, so maybe let's remove this restriction of F since we already talked about P epsilon to be a interval or to be a partition from A to C. So, I mean, can you compare the sum of these two or not? Huh? Can you compare the U and L we have on both sides here or not? Can you compare? Or can you imagine? Okay, so what should you imagine here? So let's say we have a function here like this. Okay, you want to integrate from A to B. Okay, so where is C? C is in the middle. Okay, so for F to be integrable on AB, you are looking for this difference of upper sum and lower sum here. Does it make sense? Okay, but if you consider the integrability on AC, where's the upper sum and lower sum? The upper sum is simply lying inside this upper sum and lower sum of AB. Does it make sense? Can see or not? Can see or not? So what can you see here actually? What can you see here? What can you see here? How do you compare the difference between the small lower sum and upper sum and the difference between the big lower sum and upper sum? How do you compare? Right. It's the difference is smaller, not just UFPN. Okay, it's the difference is smaller. Okay, of course, the UFPN should be smaller. So how do we pick our P epsilon then? How do we pick? How do we choose? How do we choose then? So this is what we want to show. So I need to be careful here. So here is not there exists. This is what you need to find for me. So this is what we want to show. Okay. And then this exists is given by assumption. Okay. By assumption here. So how do you define P epsilon now? So we need to define P epsilon such that, so need to define P epsilon such that UFP epsilon minus LFP epsilon is less than UFP prime epsilon minus LF P prime epsilon, then by assumption, this is less than epsilon. Correct or not? Okay, so in this case here, how we fix this P epsilon then? Minus what? P prime prime epsilon. So where's the P prime prime epsilon here? Okay, so meaning we just consider P epsilon restrict to, or we just intersect with the interval A to C. So this is how we set our P epsilon. So we set our P epsilon to be P prime epsilon intersect with AC here. Like what Zheng Kan say just now. Partition of AB might not contain C. So what do we do? We just add a C into the P epsilon prime. So if you want, we just simply add. Yeah, simply add this point C into it. Okay, so I make every such P prime epsilon into a partition that contains C. Okay, ma? It's just a refinement, ma? If it refine, right, that means this difference here could be smaller again. Could be smaller again. Okay. Does it before refine already less than epsilon? After refine surely less than epsilon. Okay, does it make sense? So this is the technicality here. OK， 所以这里是这个的技巧性在。OK， 你不能够解释，但是你说不出给别人。这里就是你怎么去证明给人家看。OK， 为什么 integrable and larger interval imply integrability on smaller interval？ 技巧就在这里，这个是它的技巧，这是个满满的干货。OK， 技巧在这里。你怎么去找这个 P-epsilon？ 你不能够整个讲，哎呀，大的可以 integrable 吗？小的当然也可以哦，因为它包在里面罢了嘛，对不对 ？But you need to show from the definition, OK? For every epsilon, you need to 找给我一个 P-epsilon partition, OK？ 怎么找呢？要做这么多的工作，没有很多啦，一点点吧。intersect 一下加一个 C 点就好了，好不好 ？Understand 吗 ？Yeah. Got any question? Any question? But how to see this diagram? Actually, you need to appreciate that sketch there. Okay, you need to be able to describe the sketch there. The sketch there is really crucial. You see how crucial is it? 我怎么可以画出那个小的 upper sum 和 lower sum 啊？怎么可以画出？如果 C 不在我的 P epsilon 里面，我是画不出的。所以我一定要把这个 C 点加进去。OK， 我才可以 compare 到。OK 吗 ？Make sense? Does it make sense? OK. OK So yeah. So picture is just help you to understand this proof. This proof is really what you need to learn here. Okay. So this is the technical point you need to learn here. Okay. How to choose this P epsilon. We haven't quite done. We only show that it is integrable at AC. How about CB? Sorry. Similar, yes, correct. So similar. 我以为你要骂我。Okay, it is also similar. What similarity here? So you just take P epsilon prime intersect with CB. Yeah, CB. And then union with CB. Okay. Yeah, similar. So this is what it means by similar. The whole step is the same, but just the choice here is a bit different. So this is why we always say similar proof, similar proof, similar proof. The whole step is the same, but the choice here is different. Just the choice is different. Set is the same. Does it make sense? Okay. Yeah. So we have shown that the tree number exists. So the tree integral here exists. And where is it? This tree integral here exists. Okay. Now we want to show that actually one of them is the sum of the other. Okay, so this is our problem now. We want to show that sum is one of the other. So how to show this? It's also very technical, actually, quite technical here. Okay, so there's some technical things to do here. Any idea? Huh? Remark some? What do you mean? What do you mean? You mean by Riemann sum? What do you mean by Riemann sum? So second step, show that integral of ABF equals to integral of ACF plus integral of CBF. Okay. So to show this, right, maybe you want something like one way to do it. Okay, I wouldn't say it's always, but one way to do it is you show that integral of b minus f is taking away the left hand side f plus cb. F is less than epsilon for all epsilon greater than 0. Okay, so this is what you want to show. Make sense? Okay. To show this, what is this thing here? I can really separate it, right? Maybe I separate like this. Is it equivalent? Yes, right? Good. This is equivalent. So how do I show this then? I want to bound this integral by the sum of the two integral using epsilon. I mean, plus minus some epsilon. So what can I do here? Yeah, how to bound this? Right. Not too clear. So not too clear, then we need to try some working here. So how to, first of all, how to bound this term here? I think you know how to bound this term, right? Yeah. This guy is equal LFUF, right? Meaning what? This is less than all the upper sum. This is greater or equal to all the upper sum. Okay. All right. And what's next? But this guy is integrable, correct or not? We already assume that f is integrable, meaning what? We can change this inequality to something like less than LFP plus epsilon and greater than UFP minus epsilon. This is how we introduce epsilon into it. Does it make sense or not? Why can I do this change here? This is integrable, right? So for every epsilon, UFP, there exists a P such that UFP minus LFP is less than epsilon. Correct? Need to write out. So f is integrable if and only if for every epsilon greater than 0, there exists P epsilon such that UFP minus LFP is less than epsilon. Okay. So we managed to introduce epsilon into this bound here. Okay. But the problem here, how you relate this UFP with this guy here, and then LFP with this guy here. How to relate? How to relate now? Relate. Like what we did just now. Hey, where's our picture? How you relate this UFP? Sorry. So how you relate this UFP LFP here with the integral of, say, AC and CB. How do you relate? How do you relate? Can you relate it? How you relate the big upper sum, lower sum to the, let's say, the half. Okay, the half upper sum, lower sum. How do you relate? Huh? How to relate the big one to the two half one? Larger, okay, sure. Can it equal sometimes or not? Sometimes. When do they equal? Sorry? N to infinity. Even before n to infinity, is there any case when these two things equal? Partition. So you need to play around with partition. So if I have a partition on AC and if I have a partition on CB, should they give a partition of AB or not? I know how to cut AC. I know how to cut CB. That means I should know how to cut everything. Okay, so if P equals to P1 union P2 such that P1 partition of AC and P2 partition of CB, then what? Then the UFP here is really UFP1 plus UFP2. Okay, similarly for the LFP1 and LFP2. Does it make sense? Can or not? Does it make sense? Make sense? I split out the sum. And then I add from A to C first, and then I add C from D to D. Then all together, I add from A to B. Okay. So up to this, if I can do this, if I can do this, then how can I relate to the Darboux integral of AC and CB? How do I relate? If I can do this. If I can do this, how to relate to the Darboux integral here? So let me put this up. If I can do it, how do I relate? Can I relate or not? If I go to this stage here, can I relate to here? Can or not? If I got this stage here, can I go to what I want? How? I got something on you. How to relate to this Darboux integral here? Yes, we already showed that it is integrable on AC and CB, right? That means what? This upper integral here should be greater than this side here. Okay. So this guy here should be go to here. And then the other side, you also have inequality like this. So we get what we wanted. Okay, so we get what we wanted here. So this is what we wanted. Want to show, right? Okay, here, want to show. We get what we want. So meaning you need to start from where? You need to start from here. If this happen, then all these things happen. And then I can get what I wanted to show here. Does it make sense? Okay. If this happen, Can this happen or not? Can P equals to P1 union P2 happen or not? Can or not? Can you find such P1 and P2 or not? Can or not? Why can you find such P1 and P2? Can you find P1, P2 that work like this or not? So what do you need to do? So the question is, can you find P1 of AC and P2 of CB such that UFP1 minus LFP1 less than, let's say, epsilon over 2, and UFP2 minus LFP2 is also less than over 2. So why do we consider this? So that if P equals to P1 union P2, what we really get is UFP minus LFP, okay, is less than epsilon. Okay, so in the middle, we got this UFP1, let's say plus UFP2 minus LFP1 minus LFP2. So this whole thing here should be less than epsilon because we want the integrability for AB. Can I find this P1 and P2 or not? The question is, can or not? Can? Huh? To find P1 and P2 such that these two things works, what is these two things here? These two things says what? F is integrable at AC and CB. Do we have that? We proved already, right? Okay, so we can find P1 and P2 such that these two works. And then the union make up the partition for AB. Okay, and then you can have your integrability property on UFP and LFP. Okay, so this is the technicality here. Okay, so the technicality is what? Find P1 and P2 such that you can define this union of them to be your partition of the whole thing. And then you can check all the property that you want out of here. Does it make sense? Okay, so people say pure maths very hard, very hard, very hard. Why is it very hard? Because you need to know what you need to do. Okay, after you do what you do, you need to check what you do. You need to check, whether this P equals to P1 union P2 give you the answer or not. There are two things you need to do. Okay, you need to be able to execute your task, and then you need to check whether you do it correctly. Okay, no, this is the two things you need to do it every time. Okay, we will do pure maths. Okay, define the things that works and then check that it works. Okay, two things you need to do. So why is it hard? Because maybe people don't know how to define, and then they GG think to check already, they don't know how to define. Second type of people is I try and define, but I don't know what to check. I also GG. You cannot check what you've done. Okay. And then the third people is you can define, you can check, but maybe you do some mistake. Okay, you do some mistake. Still okay. Okay, and then in the end, you can be a whole person. So you can define, you can check both of them. Okay. So this criteria is not just work for pure maths, this also work for all your works. All your works. If you want to do finance also can. You need to give a project and then check whether it works or not. It's the same. Okay. It's not, this ability is not just live inside this calculus. This is an ability you need in your workspace. Okay, workspace. Every workspace you need. Does it make sense? 所以如果你们每次 complain 怎么公务员做事这么慢又没有效率什么这个什么，因为他们不会数学。 OK，如果会数学的话，他会知道哦你要什么，他会直接弄给你，很快的。这就很像我们在分享一点在外国的经验啊。所以我们在外国啊，比如说我们去买OK，maybe we take a break here，break until 10:30。所以我第一天去买那个车票，我就去买车票，我不认识那边嘛，然后就支支吾吾给他骂哦，你知道吗？给他骂哦，支支吾吾给他骂，你知道吗？给那个售票员骂，因为他很 clear，他知道你来，你一定要跟我讲哦哪一个地点，然后我就按那个票给你就好了，你钱给我就是了。然后我在那边支支吾吾，因为我也不知道去哪里，可能不是很懂，然后也不知道要怎么买，所以在那边支支吾吾，所以他也不懂我要什么，我支支吾吾的时候，所以他就问我，OK，什么要去哪里啊，怎么这样？所以怎么说呢？所以我们这里要有一个讲讲啊，有效的直接沟通啊，你不会你就问啊，你就问你不会哦，到底要怎样？而 instead of 在那边又不要跟人家讲啊，然后在那边拖人家时间这样子啊，不是很好啊，因为可能这是我们的家庭的环境吧，因为可能我们父母也不属于那种人，也不属于那种人。所以就我们被怎么说哈，被这种环境下养起来了。所以为什么你的父母叫你来读书，一定要叫你来读书，让你在过上他们以前那样的生活，你知道？所以叫你多读一点书，多读一点书，就会知道哦自己哪里不足，自己哪里可以过得更好。不然你又回去你父母的生活了咯，然后你又去影响你的下一代哦，你下一代又是这样哦，做不起了这样，你整个家族做不起了，OK 吗？所以我们要读书读到一个程度，是知道我们要 come up from this norm，不好的 norm，我是说，就是讲讲 norm 陋习可能讲陋习，走出这个陋习，因为很长时候我们不知道这个陋习，或者说你父母知道，但是他不懂讲解决，他也老了，你懂吗？他已经花时间在赚钱养你了，还能够怎样去精进他自己，很难的，你明白吗？所以你父母为什么一直赚钱，一直赚钱，给你去读书，给你去读书？他希望你帮他们解决这个陋习，就算不能帮他解决，你也要解决你自己。为什么他把你生下来？可能他对这个世界还有希望，希望你成为那个希望。好漂亮。不然的话不会生孩子啊，如果生孩子麻烦死，对不对？你还要养他，养他大，他还要气你，还要气你呢，有吗？有没有惹过你父母生气？有没有？有不是？有没有被打嘛？这样讲，有没有被打过？有是不是？啊，好，yeah，right，对，那这个老师啊，我看一下啊，你 intro 啊，我感觉你 intro，我讲一些比较出名的人，比如说这种 theory 不是有看一下，我觉得你讲太仔细了，他们也是闷的。对啊，给我看一下。我觉得你的 theory 就是抓几个重点来讲就好，不要把整套东西讲，因为他们不会有回去。对啊，你讲几个容易听的、能够抓的重点就好，让他们 impress 下去这样子。这样的话，他才会继续去看，不然的话，就算你讲的很完整啊，他们 get 不到也是不是这样没有。我反而觉得你的 introduction 比较 interesting，你可以 catch 到他们，因为他们有看过那些。当然，你也不要讲太仔细啦，只是
可能一句话带过很多人，
每个老师
上后把它 link 在一起，他们就会觉得哦，我的圈子都这样连在一起，我就需要 mention 啊。然后你呢，就说我的 advice suggestion 是你的用你的那个中间的那整个盘，跟有不要整到同一个水。这重点是你要说服人嘛，所以你可以 present 1-2个部分短，就是人家这个保存能看到，因为我们时间比较短，没有提高，他也没有问出这个，所以你就
那可能可以哦。
给几条线，
那后面的时间保持多长？
不提到了吗？跟你
他们不有推荐的，如果你这样子，
好明
因
显
为他知道你的东西。你没有时间改，你直接把 playlist 拉上去就好了，反正他们也不会很注重的，就是我这个label，比较注重的是你的ID flow。
老师，我发现有个
那边怎么样？我对你的 top 呢有一个想法，就是说你把你的这个这个整个叙述讲的清楚一点，然后他们认识的人的那些做了什么呢？然后领导那个提也是说，哎，看这个 architect 和 roles 有，然后那个 cascade 当然你要 define 咯，因为后面你可能要求他这东西讲稳，所以最重要的一些 definition 你丢给他。那些 method 的话不用太仔细了，就是用 example 带，用 example 带，把它讲清楚，因为他们肯定。当然对呀，做数学还是很的。当然我们要完成好的是你在做的时候，你要想办法。
讲过，讲过。为什么？接下来是有 reference 还是那种有用过的？
然后那个线条那个图的。
把这个然后最靠近不光就是原则，然后
这样的话，你要point out它的积分在每句上出来。
我是啊，我就是还是从就是用那时候是以后每次讲，如果是差不多3个月，我还有一个就是在19多年代，有一些人会觉得，哎，这可能不是东西。因为他们这是找到一个点，还有一个比赛，那一提了结果另外一个事情就有个是怎么解决？然后再讲例子。
那个步骤你讲过了之后，做一个example，他们可以切入因为也不可以不说那个步骤，因为人家如果要知道，他也要有一个在他的理由和部位的切入，对，这样要 spend 太多时间解释你的那个 general 的那个我的 advice。
我甚至都就直接来跟他讲，这个就是这是脑子全是讲的是说这样不对，然后我就在 就拿idea 的那个方法来讲那个 solution，所以首先如果有个 formula，就是那个全部都这样子，如果有 formula 可以找一个方法，然后就做了一个 transformation， 这样的那个 transformation 我们就知道我们要治理的，然后呢，把这个 formula 感觉。然后我们手下面字，然后顺便就讲，现在上一个那个 point， 我们的入口那个就在这边和这边那边
画出来，
下午的。
你比如画出来，感觉对，哎，你要现场画吗？你可以现场画，你要把根画来。对，哎，我有给一个advice给你在你的那个 project 里面是说，摔了这东西过后，哎，跟我们的螺旋有什么关系？啊，不然我们穿这个来给我。对，所以它那个 root 是不是那个 row 里面那个 f prime 零那个？
有类似的单词，就是
因为它 root 了嘛，它一定要回来嘛，对不对？所以它回来了就变成我们现在讲的那个东西了。因为不然的话，它 root 下去了，怎样会有另外一个 root？它肯定somehow它要跑回来嘛。等它跑回来的时候，它一定遇到一个 maximum 或 minimum， 然后那个就是现代版的 rotor 嘛，对不对？开图听一下，要不然我听了你这样多，我找了这个 root， 人我的现代的 rotor 跑哪去？你可以用几句话带过就好了。但是我觉得你可以在你的 project 写清楚，因为不然的话，你的 root 可能就是 pop 一句，然后后面全部是就在东西就完了，就没有这个。
像我
知道你有 history 的联系，但是history 本身的联系应该是有东西要讲的但是如果要去 prove 可能又很麻烦了，不用 prove 了，但是至少要 stay 这样。我觉得你画了那个什么图过后，那个 F prime 的那个 part 就会跑出来了嘛，然后你就可以 point out 哦，这个 maximum 或者这个 minimum 就是我们现在把 row 讲的关的因为你的东西看。
感觉你不是
季节，面临季节。
我就管它少下去了。
我们开做了，
不然两方都没有很难。
那你是什么时候？
就是那个学校的课程有没有？
是。
Testing. Okay, let's resume. Hey, where's the rest? Go ahead. Okay, by the way, this proof I'm put into the lecture notes, so please go back and read how I phrase it. Okay, because when we discuss and how we phrase it, it's a bit different. Okay, when we write out the proper proof, the order different. Okay, because when we want to solve a problem, we always start with the endpoint. 我们要解决的是那个症结点嘛，所以 endpoint。But when you want to present 我们是从头到尾讲给人家听的，我们不是从尾到头写出来 ，OK？ 但是我们现在去讨论问题的时候，我们肯定是要解决症结点先。Okay, so this is a bit different when we present and when we write out the proof. Okay. Right. So I mean, for the rest of the property, I would let you to do it yourself. If we have time, we can revisit it again. For example, in a revision time or what. But I want to present a few proofs to you before we jump to next section. For example, I want to show you this proof here. What is this proof? This integral mean value theorem proof. I want to show you because it has a very nice use of a theorem that we have learned before. Okay. So what's this this integral mean value theorem tell us? Remember what the what what Jack drew to us last time? What does this mean value theorem tells you? If you have a graph, right, and then there has this C, there has this C, such that what? Such that the area under the graph and above the graph is equal. This is equivalent to saying that the area under the graph is equal to a rectangle with height FC and length BC. Okay, because if you cancel out the bottom rectangle, then this is what you get. Not bottom rectangle, but cancel out the part that have the same area, and that's what we get. Does it make sense? Okay, no? Okay. Okay, so how to prove this? Okay, so in first slide, how to prove this? So what's the idea here? What's the idea here? Idea here is, of course, you need to evaluate this guy, this Riemann, this Darboux integral guy. Okay, we need to evaluate it. Okay, let's see what is this number here. So how to compute this number? This number is equal to the upper and the lower sum. Okay, upper and the lower sum. Sorry, upper integral and the lower integral. Okay, not just upper sum and lower sum. Then, what do we do here? What do we do here? Can you bound this integral? No, not. Can you bound this integral? Can I bound it? Maybe if we cannot bound integral, can we bound the value of f or not? See, here f is integrable, but this question here got extra condition of f. Is what Joshua won just now. F is continuous. This guy is continuous on a bounded interval. Closed and bounded interval means what? It attains maximum and minimum by extreme value theorem. So fx here is less than some lower bound and less than some upper bound and greater than some lower bound. Okay, so you can use the what's that? The property of integral to find that. Find what? The integral of AB of fx is less than equal to the integral of AB of m and integral of AB of little m. Okay, does it make sense? So you can see that if you move b minus a, you move b minus a from all of them, you can get that. What do you get? You can get that this number here, 1 over b minus a times integral of f from a to b is less than equal to m and less than equal to m. So what's the next thing we like to show? We want to show that there's some f that attain this number here. So how do you show this? How do you show that f can attain some number between two numbers? What's the theorem that gives you that? What's the theorem that says you can attain some number between two numbers? Intermediate value theorem. You can reach the intermediate value, right or not? You can reach the intermediate value. But to do the intermediate value theorem, what's the condition you need? FA equals AB. No, that one is a mean value theorem. Either FA less than FB or FB less than FA, something like that, right? Otherwise, there's no middle value for you to reach if FA equal to FB. Fair enough. So FA maybe less than FB or FB greater than, so less than FA. Okay. And then F have to be continuous. Okay. But here is M and M. Is this M and M, is this small m and big M some value of F or not? Is it some F of something or not? Are they the image of F, in other words? Yes, right. Because how we find this small n and big M? This is from the S string value theorem. What does S string value theorem say? F must attain maximum and minimum. Attains means what? This maximum and minimum is the image of some image of some point. So, in other words, what we have here is this one is an x mean, fx mean less than this integral here of fx dx less than of some f of some x max here. Okay, so by intermediate value theorem, there has this sum c such that fc equals to the middle guy here. Okay, does it make sense? So this is a very good use of extreme value theorems and intermediate value theorems here. Yes. Where? Oh yes. Sorry, I missed it out. Yes. So, yeah. Okay. What question or not? Any question? No. Okay. And also this fundamental theorem of calculus here. Okay. Last time I told you the significance of this fundamental calculus. So what's the significance here? Last time I introduced to you that in your calculus calculation, the calculus of integration is a calculation miracle. What do I mean by calculation miracle here? Why if I differentiate? Why do I differentiate? Let's say if I want to integrate x squared from 0 to 1, how do I do it? Your thinking is I integrate x squared first, and then I evaluate from 1 to 0. But this fundamental theorem tells you the other way around. It says that if the big F prime is equal to x squared, so meaning what? You need to make sure that the derivative of x squared over 3 is x squared actually, so that you can perform this integration. So this is the difference between if you learn analysis or you didn't learn analysis. Because high school asks you to integrate first. But what's integration? You remember integration just by law. What's the law you use? I add the power first by 1 and then I divide by that power. But what is that? That is the reversal of your derivative differentiation. Okay. So the theorems read like this. Is if you know that the capital F has derivative of small f, then you can do this integration. Okay. So meaning what? Meaning what you need to know is you need to know this part first. Okay, only then you can do integration. So this is the order different. Okay, order different when you do integration in calculus. Does that make sense? Yeah. No question? Okay, so in this case here, how to prove this guy and how to prove this. So this is the thing you always do in your calculus. But why is it true? Why is it true? Actually, this proof uses a mean values theorem. Okay, it uses values theorem here. Okay, how should we use it? How are we using it? Okay, how are we using it? Okay, same thing here. So you want to show that these two number is the same. What do you need to do? The difference is less than any epsilon. Okay, the difference is less than any epsilon. Okay, good. So, I mean, another way to do it is maybe you could, so let me move the other guy down, then later we can discuss about it. This guy. Okay, so maybe put a proof here. So we want to show that fx dx equals to fb minus fa. Okay. It is also equivalent to show that fb minus fa is less than uf and greater than ff. Okay, if I can do this, also can. Why? Because our function is integrable. So that means UF have to be equal to LF. So you are bounded by two same number here. Also works. Okay, if you want to use the epsilon where also can. Okay, also can. But in this case, we can do this as well because we already know that UF equals to LF. Does it make sense? Make sense or not? Okay. Okay. So how do we do this? So how do we do this? Why do I say that we need mean values theorems here? What does mean value theorem tell you? And what does mean value theorem tell you? So it relates the function with its derivative. So here we also have relation between function and derivative. Okay, so this gives you a hint to use mean values theorems. Okay, so how do we use it here? So I mean, to this end, let's look at this guy here, and then I'll show you some miracle. So since we need to deal with LF, UF, right? So let's just start with a random partition. Okay, we just start with a random partition here of AB. Okay, we just start with a random partition here. Since F is differentiable, okay, by mean value theorem, there exists a Ci in xi minus 1 xi such that f prime Ci is equal to s xi minus f xi minus 1 and xi minus xi minus 1. Okay, so far everyone okay with this one? So far okay or not? Mean values theorem. Okay. Later, now I'm going to show you how it relates to little f. Okay. How does this relate to little f? By assumption, this f prime c1 is what? Is just little f c1. So all together here, what do you get? You get a relation between fx I minus fx I minus 1 equals to fci times xi minus xi minus 1. Okay. Wait, a bit like what? This one, this xci and this xi minus 1, a bit like what? Like Jingsen, I think you have more experience with this one. More experience. But how does this look like? This C1 is in between xi minus 1 and xi. FCI and this interval is what? It's something from the Riemann sum. Xi minus 1 is the width mark. FCI is the length mark. But how you decide this length? This length here is random CI indeed. This is part of the Riemann sum. So how do you estimate Riemann sum? 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 It is bounded below by what? Infimum, the lower sum. Okay, lower sum. The book's lower sum, and bounded above by what? Bounded above by what? Supremum, the upper sum. Okay, the upper sum. This is true for any interval, right? Subinterval. So what I can do is I sum all of them. I sum all of them. If I sum all of them, left hand side, what do I get? The lower sum. Okay. The right hand side, upper sum. What's the middle here? It's a Riemann sum. But more importantly, how do we know about this Riemann sum? How do we know about this Riemann sum? Go back one line above. Riemann sum is a telescopic sum of this capital F. Is it a telescopic sum? Huh? Telescopic sum, right? If you plug I equals to 1, what do you get? fx1 minus fx0. fx2 minus fx1. So what do you left in the middle here? What do you left with? fx n minus fs0. What's this? What's this guy here? fb minus fa. And this inequality is true for every partition. It is true for every partition. So meaning what? Since the inequality above is true for every p, okay, then the supremum of f should also less than equal to the fe minus fa, and the infimum of ufp also have to greater or equals to fe minus fa. Why? Why? We use the infimum and supremum property again. Because fb minus fa is one of the upper bound for your lower bound. So the supremum must be less than this upper bound. Because supremum is the lowest upper bound. U is the infimum. It is the greatest lower bound. So since fb minus fa is a lower bound of your upper bound, lower bound of your upper sum. Yeah. So your greatest lower bound must be greater or equals to this fb minus fa. Okay, no? So we go back to the theory of supremum and infimum. Okay? Nothing fancy here. Okay. So in this case, are we done or not? Are we done? Done or not? Done. Because since f is integrable, uf equals to lf. So you bounded by two same number here. Okay, so if you bounded above by the same number, then you are the number itself. Okay, no? Yeah. Okay. Okay, good. Okay. Any question so far? So this is how we prove the calculation miracle you use in calculus. You need mean value theorem here. Okay, you need mean value theorem. So it's very important, mean value theorem here. Okay. Any question so far? Okay, the next bit here, maybe I don't want to discuss about the proof, but you need to know about this result because this is how we define the function ln x. Okay, how we define function ln x. is exactly we define ln x to be the integral from 1 to x of 1 over t dt. Okay, because remember, if you go and look at my tutorial 8, I suggest you to look at tutorial 8. Okay, tutorial 8 is how we define the derivative of ln, natural logarithm, exponential function, trigonometry function. Okay, and then I put inverse trigonometric function in as well. Okay, all of them, arcsine, cosine, those functions. Okay. So how do we define? Is using this. So if we define ln x to be the integral from 1 to x of 1 over t dt, I need to argue to you why derivative of ln x is 1 over t, 1 over x. Then this theorem tells you if I differentiate the integral of gt, then what? Then the answer is just the function in the middle of the integral. Okay. I think Lord How know this very well. Right? You're gonna tell us tonight about this FTC, is it? Okay. Seemingly, if you can listen to his talk tonight, this is where Newton care about this derivative. Okay, so he is looking at some area under the graph and the relation with the derivative on that graph or on that area. Okay, how the area changes. Okay, with the function that you're looking for. Okay, the function that bound the area. So there's relation here. This is that relation. So if you think about the integral, right, using area, so integral from a to x, so you can think that that area is like increasing with x, for example. Okay, and then how this, you can think of it like if your function is increasing, when you increase x, what happened? Your area also increase, right? So you ask the question of what's the rate of increasing of this area? Right? The answer is the same as the function you started with. Oh, then derivative of that area is equal to the function that you integrate for. So this is the idea of the FTC at first. Okay. How does the rate of area relate? Okay, what is the rate of that area under the graph? Is exactly the graph itself. Interesting, huh? Okay. Yeah. So how to prove this is a bit tedious. Why I said a bit tedious here? Because what do you need to do? How many things you need to do here? This theorem is good. I already defined for you. Not need to go and find already. Okay, I already defined for you. But what you need to check here? Check that first. G is continuous. Okay. Second, not yet before integrable. If the small g is continuous, you need to prove that this g actually differentiable, not just continuous. If it's differentiable, you can compute the derivative, correct or not? Prove that this derivative is actually the small g you started with. Okay, so this is the content of this fundamental theorem of calculus. So there are 2 things or 3 things you need to do. Okay, 2 to 3 things. And I have put the proof inside my lecture notes. Okay, and you can go and try and read. So basically, that proof involve property of integral, and then just differentiability. That's all. Not too hard, but it's a tedious track. Okay or not? Differentiability and continuity. Okay. Okay. Good. Let's see. 1, 2, 3. Okay, so far up to here, any question or not? Any question? We have run through what we have did last lecture. Time is it? 2 o'clock. You guys have energy to listen more before break? Okay. Okay, let's go a bit further and then we'll see how. Okay, so next thing we're gonna do is integration by parts. Okay, so what's the integration by parts? I think you give me one question to do. So what's integration by parts? Well, give me a question. I give some motivation here. Integrate who and who, so that we can use integration by parts. 来 set 一个问题给我 cos ex 啊，下手这么狠 ，ex 乘 cos x 嘛 ？OK， 好。Okay, let's integrate from 0 to 1 because now we learn definite integral. So what do we do here? Okay, tell me how to set u equal to x and then v prime or v? Okay, v prime. Derivative, I set it as a derivative. And then? Huh? Oh, differentiate du. Okay, sure. Differentiate du. So we get dx, right? Okay, and then integrate v. So v, what do I get? Sin x. Need to plus c or not? Also minus. But need to plus c or not? Why not need? Because later will cancel out actually. Actually you need, but later will cancel out. Okay. Okay. And then equals to what? The uv. Sure. So in this case it's ex sin x minus integrate. Okay, integrate from where to where? v du. So it's ex sin x dx. We're not done, is it? Need to continue. Sure. So in this case we have ex. So let's skip the step. So can you tell me the final answer? Minus what? Ex cos x? Need minus or not? Need minus. And then plus ex cos x. Is it like this? Yeah. And it looks wrong. What's wrong? Minus. Should be minus because there's a minus cos sign, right? Minus with a minus. So where's the other minus? Oh, the other minus is coming out from the original minus. Then you have a previous minus. Then you have a cos sign minus. So there are 3 minus. Okay. So this sounds better. So in this case here, you get integral of ex cos x dx is equals to the half of the sum of these two. Okay. What's the sum of these two? Huh? What's the n answer? Oh, you cannot evaluate, is it? Okay, so e to the e times sin x, so sin 1 minus. Oh, this one is a bit long, is it? E to the cos 1 plus ex, like this. Like this. Something like that. Correct or not? Huh? Cos 0 is 1, right? Oh, E0 is 1. Okay, good. Okay, good. Like this. Okay. Yeah. So what have you used here is really this. So if you differentiate fg prime, you will get fb minus gb minus fa ga. Evaluate, okay, evaluate the integral you get, and then minus integral of fab minus f prime g. Have you wondered where this from? Where this formula from? Yes, product rule, correct. Product rule. So you start with product rule. Okay, you start with product rule, and then you integrate all of them. Okay. So I mean, to integrate all of them, right? You need to make sure what you need to make sure all the term inside the product rule is integrable. Okay, you need to make sure all of them are integrable. So to make sure they are integrable, you need to just make sure that fg prime and f prime g are integrable. Why fg prime and f prime g are integrable? So you need to use the condition on f and g. Okay, you need to use the condition of f and g. So f and g is what? Differentiable, first of all. And then their derivative is continuous. Continuous. So fg prime, in particular, fg prime and f prime g is what? Are continuous. Okay, because differentiable implies continuity. Okay. But derivative assume that it is also continuous. So these are product of continuous function. Okay. So we have proven that every continuous function is integrable. Okay. So in particular, their sum is also integrable. Okay, integrable. So what do we get is integral of fg prime equals to integral of fg prime, sorry, f times g prime plus integral of f prime times g. So is this close to what we want just now? Is this close or not? So that's why you have a minus sign, no? Because you move this integral of a b f prime g to the other side. That's why you got this minus sign. But how about this part here? Is this the evaluation of fbgb minus faga? Is it? Integration can undo the derivative. What's this? This is the fundamental theorem of calculus. Integration can undo the derivative, right? So the integral of this derivative is exactly fgb minus fga. Go back to the statement we have for FTC just now. You see? So the slogan you need to remember for this fundamental theorem of calculus is the integral can undo the derivative. You see, you integrate f prime x, what do you get? You get back your f. Can you get what I say? Okay, let me remove this. So if I rewrite this guy, here, integral of f prime x dx, what do you get? You get fb minus fa. You undo the derivative. Okay, you undo the derivative. Does it make sense? 知道什么是 undo 吗？知道啊 ，Microsoft Word 上面有一定 undo 是不是？回去 ，OK， 从哪里回去？从 f prime 回去，打 f。Okay, undo. So they're like, you can think of it like cancel. Okay, you can think of it like cancel out, something like this. Okay, but when you cancel out, you get fb minus fa. So it's the endpoint. It's the right endpoint minus the left endpoint. Fb minus fa. Okay, after you cancel it. Does it make sense? Okay, so this is, you can think of it how you remember this theorem here. All right. Okay, we have proved these integration by part. What is the next? What's the other thing you do? What's the second technique you use? Integration by substitution. Why is it true? Why can you use integration of substitution? Give me a question. Give me an exercise, a problem to solve by integration by substitution. Any question? in your mind that you can use integration by substitution? Okay, 一个比一个很难。Like this 啊 ？OK， 好，我不会哦。OK， 来，come， 都说了。来 ，actually not too hard maybe. 来 try. Okay, u equals to cos x. Negative. Okay, negative. Sin x negative. Sure. Okay, and then over u square. Sure. Divide. Supposedly you get 1 over minus sin x du, is it? But you don't want this minus sin x to involve again, right? Any way to get rid of it? Need some triangle or not? Let's see. Maybe need, huh? So let's do some triangle business here. So what's this triangle business? We have this sign here. So cosine x equals to u, it means what? Cos is what? Adjacent over hypotenuse. So adjacent should be u, hypotenuse should be 1. So the other side, opposite, you get square root 1 minus u squared, right? So sine x becomes what? Opposite over hypotenuse. So square root 1 over 1 minus u squared. So the bottom here becomes negative of square root 1 minus u squared here. And then you need to integrate this from 0 to 1. Okay, so let's stop here. Okay, yeah. So so what's the point here? Okay, the point of talking about this substitution is we introduce this part here, dx. So let's rewrite this. This is dx equals to 1 over minus square root 1 minus u squared du. So you introduce this extra bit here. Okay, so you introduce this extra bit here. So how do we rephrase this? So with the integral of f gx g prime x is equal to the integral of fw dw, where what was this w here? Oh, this w is this substitution just now, u, right? Just now we use u. So we set w to be gx here. And then you change the integral domain. So in the above here, right, we should also change this 0 and 1. So when x equals to 0, u equals to 1. When x equals to 1, u equals to cos 1. Okay, so you need to replace this integral here from where to where? From 1 to cos 1, like this. Okay, make sense? Okay, so why is this true? Why is this true? Why is this true? You can go back and see also. Okay, I write down the proof already. Okay, it's in the last week lecture. Basically, it uses FTC a few times. Okay, yeah, it's quite nice. The proof quite nice. It's a good use of FTC. Okay, so I would just say that this proof uses FTC. Okay, then try go back and read through. Okay, so far we have covered how many things we have covered. We have covered all the way from the book sum to Riemann sum. Okay, and then we treat it properly in our tutorial and assignment. And then this link back to your calculus one. So all of these fixed together already. And then after we define the book integral, we check the property. Okay, for example, if my function is positive, integral positive or not? What is the what is the integral of sum of function, scalar multiple of function. Okay? And then we check all these property. And then what else we check? We have this integral mean values theorem. Okay, a bit similar to the derivative mean values theorem. And also, what have we proved just now? FTC. FTC is the main thing we did in this chapter here. This is exactly what you did in your high school. So in your high school or secondary school, we ask you to do the calculation machinery like a machine. You really just do it like a machine. You don't know why is it true. So now we teach you why is it true. FTC is true. And then after that, you also learn some machinery item, for example, machinery step, for example, integration by parts, substitution. Why this word? Okay, this word is because of FTC. Okay, we prove it. Okay, using FTC. Okay, using FTC. Okay, so all these important method follows from FTC. So FTC is the main thing you need to master inside this chapter here. Okay, it's the main thing you need to master. And before we end this integration subtopic, I want to talk about how to define these two items here. Maybe not writing it up. So let's define it. Okay. So we want to define infinite integral and improper integral because later we will use it for our Taylor series, something like that. So we will end our subject or our course this semester, hopefully in Taylor series. Okay, it's a bit similar to what we did in calculus 2. We want to show convergence. Okay, so we will look at sequence of function. So the one last chapter we will look at the sequence of function because at first we learn what sequence of number. Okay, sequence of number, and then in the last chapter we will do sequence of function. How do you think about sequence of function? You can think of last time how we approximate a function using Taylor polynomial, right? If we add more terms, you can see that the function get closer and closer. The Taylor polynomial get closer and closer to your original function. At the radius of convergence, okay, within the radius of convergence, it converges. So to that end, first we will define what is it? So we'll define what is an infinite integral here. Okay, what is the infinite integral here? So basically, I only define integral for a, b, where a and b are finite. But now, let's say one of them is infinite. Huh? What kind of integral looks like that? Yeah, this integral here. If you want to integrate this guy, how to integrate? Okay, how we treat infinity? This concern with how we treat infinity. 怎样去到无限？告诉我。Elon Musk 的火箭。怎样去到无限？ How to go to infinity? Sorry. Okay, limit. Okay, limit of a number go to infinity. So in this case here, we will take the limit of this integral here go to infinity. So for example, what you can imagine. So you can imagine that I take integral from a to b plus 1, a to b plus 2, a to b plus 3. Correct or not? Because all these are integral that I defined before. So you need to make sure that f is integrable. Integrable way. Integrable on what? On every closed interval a, b, such that b is greater than a. Okay, so that all these integral will define. And then this integral define meaning what? I get a sequence of number. So if it is a sequence of number, then I can look for the limit. Okay, so this is how we define the infinite integral. Make sense or not? Does it make sense? Okay. Okay. So when we take limit of integral, it just means that we are taking limit of sequences of number. Okay. because each definite integral here is a number, and then I look at the limit of this number. Can or not? Does it make sense? Once you have a sequence of number, you can look at the limit, whether diverge, whether converge, whether what. Okay, does it make sense? Okay, too easy or don't understand? Can understand what I said? Can okay. Okay, if too easy, you also not 点头一下，然后我讲比较快一点啊，不然的话我也不知道你懂还是不懂啊。如果不懂的话，你记得问啊，因为不然我不懂你不懂，你没有问的话，OK， 所以你还一定要问我 ，OK 吗？ No question? So far okay with this limit here? Okay, so let's go to example. Example here. Let's say I have to compute 0 to infinity of this point here, of this function here. How to compute this? By definition, this is the limit of v go to infinity of this definite integral here. So we compute what's this integral here. So we define arctangent x to be a function that have derivative 1 over 1 plus x squared. Okay, this is in my tutorial ad. I suggest you to go and read my tutorial ad because that is the rigorous treatment of trigonometry function. Otherwise, you wouldn't know what is the derivative of arctangent x. We define it to be so. Okay? Otherwise, you wouldn't know. Okay, so that's why you treat it as a formula inside your calculus book, okay? Because we define it to be so. So we have to look for this limit of this evaluation here. So what is arctangent v minus arctangent 0? Arctangent 0 is what? Arctangent 0 means what? It's the inverse image of 0. What's the inverse image of 0 for tangent? Rho also, right? Okay, so it's 0. I mean, depend on how you take the the interval of your tangent, okay? But no matter where you take, it's still 0, right? It's not. Depend on where you take the interval. If you take from 0 minus pi over 2 to pi over 2, then it is 0. If you take different interval, then you have different pre-ratio. But anyway, what is arctangent b here? When b go to infinity. So when b goes to infinity, what is the pre-image? If you take minus pi over 2 to pi over 2, then it is pi over 2. Okay, depend on where you take this tangent. So this answer here, this answer here will depend. So take tangent x to be okay. Any questions so far? Okay or not? Okay. So if we take like this, then we get pi over 2 minus 0, which is pi over 2. Okay, the another integral we want to define is called the improper integral. So how do we use improper integral here? How do we use improper integral here? So improper integral here, maybe we're using this kind of condition. Okay, let's see this condition here. Integral from 0 to 1 of 1 over square root x dx. If I straight away use fundamental theorem of calculus, what do I get? What do I get if I use fundamental theorem of calculus? So what's the guy that has derivative 1 over square root x squared? 来，算一下，谁的 derivative 是它？ 发了，就这样，没有减，没有什么的，没有哈，没有哈。哦，OK，就它好吧。Square root x， so 还可以。So if I evaluate from 1 to 0, I see. What do I get? I get 2 minus 0. 诶，还可以算到东西。But 但是有一个问题 ，there's a problem here. This function here in the middle here is not defined when x equals 0. It's not defined. Why is it not defined? What happened here when you go to 0 from the, let's say, from the left, from the right? This function shoot out to infinity. Okay, this function shoot out, okay. So technically, we cannot do integral on this 1 over square root x because every time we do is on a closed interval, right? But this guy is not defined, not even defined at 0. So how do we settle this problem? Away from 0 is you still can integrate. Away from 0 you still can integrate. So what do you do? Hey, this one I think I make a stupid mistake here. So I think it's like this. So okay. So what do I do? So away from 0, I still can calculate the interval, and then I take limit all the way to 0. Okay. Okay. Yeah. Okay. So this is how we define the improper integral here. Okay, because our function is not defined at that point, what we can do is we take limit all the way until that point. And we check the integral. Hey, it's quite, don't you think this one is quite magical, right? Don't you think this is magical? What is 1 over square root x? Looks like this. And this one shoot to infinity, you can still find number is 2. Crazy, eh? Crazy, eh? But this is not true anymore for 1 over x. If you try integrate, if you do improper integral for 1 over x, then what you get ln y, then you will diverge. Is it? Yeah, you diverge. Okay. So meaning what? This 1 over square root x, it increased quite small. Small until somehow you can cancel with the infinity part. I mean, yeah, decrease quite fast until you can compute it. Integral. Okay. Yeah. So this thing has to do something to do with the rate of decreasing. Like if 1 over x not that fast, the integral will diverge from 0 to somewhere else. Okay. Yeah. Right. Somehow we're finished here. What time is it? We only have 20 minutes. Yeah, so far any question up to here? Any question up to here? So I mean, what's the deal with improper integral and infinite integral with the integral we define? What's the deal? What's the deal here? Huh? What's the deal? What's the deal? How you connect the idea between improper integral, indefinite integral with the integral we define? What's the deal here? Yes, we're taking limit. Okay, we're taking limit of this integral. So we treat the integral as number now, and then we look at the limit of this number. Okay, no? Yeah, that's all. So we combine the, wow, how many things we combine? We combine, so how we define integral? First of all, supremum, infimum. And then we look at the sequence of this supremum, infimum. Okay, so everything come back to first few weeks. Okay, sequence of number. Okay, then now we are looking at sequence of supremum or sequence of infimum because they are equal. if they are intergroup. Okay, sequence of superhuman, sequence of infinite. And then we look at their limit. So everything come back to first few weeks now. So we are using everything are using what we have built. Hey, in that case, we just continue lah. Only 20 minutes only, then we off already. So next chapter, before we jump to sequence of function, we will quickly review infinite series. Okay, remember what's infinite series? We did in calculus 2. Remember the chapter, the first chapter we did in calculus 2. There's a lot of tests one. Ratio test, root test, simple comparison test, Hambalan test. Hambalan test. Okay. So those tests, right, we will revisit them, okay, quickly review them. We won't do much example, but we will prove the test that we never proved before yet. Okay, we have proved a few of them, but most of them we haven't proved it. And then we will introduce two more proof. One is Abel's proof, one is a Dirichlet proof. Okay, so these two tests here will deal with series that is a product of series. Later I will show you. And then hopefully we will put this example into your tutorial and then you can do it. Okay, how to use this test. For other tests, go back to calculus 2, pick it up. Again, dig it out and just read through. Because we need this test to show some convergence inside the last chapter. Okay, that's all we need to use them. Okay, we won't have much tricky question on this chapter. Okay, we just quickly review them. Okay, let's look at some of them first, and then we will continue tomorrow. Hopefully by tomorrow we finish this infinite series, and then how many weeks we left? 13, 14, 15. So hopefully we will spend this last 3 weeks on the sequence of function. And if we can manage to finish earlier, then we can spend time doing exercise together. Okay. Yeah. Right. Talk about series. So what is series? So series is another level above sequence of number. What do? You start with a sequence of number and then you add them up. Okay. You add them up. So the infinite series is defined on a sequence of number where you add them up. Okay, you add them up. There's infinitely many terms inside your sum. So to study the convergence of this infinite sum, what do? Remember, we define a partial sum. So what is A1? What is A1 plus A2? What is A1 plus A2 plus A3? Plus A1 plus A2 plus A3 plus A4. So these are n partial sum. Okay. So if we want this infinite series to converge, if the partial sum converges. Okay, no? Why we look at partial sum? For finite sum of number, the number is finite. There's only finite, right? There's only finitely many numbers you need to add up. Maybe it's very large number. Then we can look at the limit that built up by the sequence of this n partial sum. Okay. Again, go back to the idea of limit again. Okay, sequence and limit. Okay, look at the sequence and limit. Right. And then if it converges, then it converges to some number, we call it the sum of the series. Okay, if it diverges, if the n partial sum diverges, then the series diverge. Okay. Diverge could means a few things, right? Maybe diverge to infinity, or it alternate between some number, minus 1, 1, minus 1, 1, minus 1. Right. Remember, there's a sum that add 1 and minus 1 together. How do you write that out? For example, the sum looks like, let me see. Okay, this one should be 1. And so what's the sum of number that have alternating minus 1 and 1? Okay. How to write that down? that down. So okay, let's write down the partial sum. Okay, so partial sum. What do we want? Can we get something like this? Or or can we like put in some zero in? Can or not? So can we define some sequence of number that give us this? So I was thinking like this at first. So if I get this in this case, I'll get different stuff, right? Instead, I'll get 101010 instead. Okay, so we get 1010. How to write this down? Is there a way to write this down? And I think we don't have a nice way to write it down other than write that an equals to -1 to the power over n, or n plus. Okay, yeah, this guy diverge. Yeah. Hmm. The n partial sum diverge. Alternate between 1 and 0. Okay. 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 Yeah. No question? Question or not? So far? Okay. Okay. If no question, next part. So what's this next part here? Can everyone read this together? Read this together. Let k in n. Okay, and then let this sum is summing from k to infinity. What does this mean? K to infinity means what? I throw away the first kn k minus 1 term. Then this series either converge or diverge together with the original series. What's this deleting doing? I deleting the finitely many term in the front. So meaning I look at the tail. Okay, I look at the tail. So I have to prove that this series, so the deleted series and the not deleted series converge or diverge together. You know how to show this? Okay. So, and what we can do is we look at this. So you want to show convergence or divergence, right? So for infinite series, you need to always go back to the partial sum. Okay, so that's how we introduce partial sum. So if you look at the partial sum from k to m, what is this guy here? This guy is all the way from 1 to m minus all the way from 1 to k minus 1. Okay. Okay, so far. Okay. So if you take limit on both sides, right? So if you take limit when m go to infinity, this side here is the tail that you look at. And then on this side, then what happens? If you take limit from m to infinity, you see this second term here doesn't depend on m. Okay, so this is some number. Okay, but what is depend on n is this limit here. Okay, so meaning that the limit on the left hand side exists if and only if the limit on the right hand side exists. In particular, this is the infinite sum. The series. Okay. Okay. So since this is true for all k, then this is proven for all k. K and n. Okay. Does it make sense? Okay. This is a very good check. This is a very good check. If you throw away, so how we use this? I remember how we use this in calculus. How we use this is if we know that the infinite sum converges, Then even if I throw away first few term, it also converges. But in here, we show that both also diverges. Okay, if one of them diverge. So we have extra result here. Okay, does it make sense? Okay, if your series diverge, you throw away first few term, you also diverge. No help. Okay, there's no help to reduce the divergence. Okay, no help. Okay, second part here is we also make this precise. If your series converges, your tail also goes to 0. Okay, the tail also goes to 0. What's the tail here? So the tail is what we did just now. We throw away first few k minus 1 term. Okay, if your series converges, then this sum here will also converge to 0. Okay, so the tail here goes to 0. When you take limit goes to infinity. Okay. It's a bit different with the divergent test. Remember what's divergent test? If the series converges, then the limit of an goes to 0. But here is the sum of the tail terms. The sum from ak to infinity. This thing converges to 0. Does it make sense or not? Let me write down. So what we have here is if sum of ak from infinity converges to 0, then what? Then A1, for example, A1, A2 plus A3 plus A4 plus A5 plus dot. And then you can look at the series of the tail. So for example, A2 plus A3 plus A4 plus A5 dot plus dot. And then A3, A4, A5 plus the rest. And then you're deleting the first few terms, okay? And then this series converges to 0. It's the sum of the tail. Okay, but in the divergence test, what you get is A1, A2, A3, A4, and so on converge to 0. Each term converge to 0. Okay, so this is in divergent test. Okay? But in this statement we have just now is the tail of the convergence series converge to 0. Does it make sense? Can you see the difference or not? Can you see a difference? Hello? See a difference? Okay, just now we are talking about the tail of convergence series converge to 0. And then divergent test, you look at the limit of each term converge to 0 when n go to infinity. So in this case here, when n, so let's denote this as an go to when n go to infinity. The other side here, we have ak plus ak plus 1 dot, when k goes to infinity. Okay, so this is the difference here. Okay, make sense? So how do we prove it? How do we prove this tk goes to infinity here? So you need to compute what is tk. Okay, how to compute tk? tk is the infinite series throw away finitely many terms. Okay, so this is tk. And then you need to take the limit of tk. So if you take limit on both sides, does it exist or not? Does it exist? This guy here is what? It converge, right? Converge meaning this sum here is a number. Okay, just a finite number. So when you take limit, really you're just taking limit of this guy here. Okay, from 1 to k minus 1. Okay. But if you take limit of k minus 1 from k to infinity, means what? this term here should approach the sum of series. So sum minus sum, you get 0. Okay, now because converge, then this is really the sum. So s minus s is 0. Okay, does it make sense? So what I want to say here is limit of k goes to infinity of tk is really what? X. So it's really sum of n minus 1 of infinity an minus sum of n equals to 1 to infinity of an, which is just 0. Okay. So this is how we prove the tail, again, the tail of the convergence series equals to 0. Okay. Make sense? Okay or no? Okay. Okay. Last 3 minutes. So please go back and try and revise what is in the calculus 2. Tomorrow we will prove all of them. We will try and attempt to prove all of them. Okay, if not proof, then we just do a proof sketch. Tell you why roughly it is true. Okay, what is the technique we use? So the technique we use would be really basing on epsilon delta sum, epsilon sequence sum. Okay. So we will go through test for divergence, P series. P series geometry series we prove quite detailed in calculus 2. So we will skip it. Test of convergence, we also did it, so we skip it. Comparison test, I think we did it, and then we will skip as well. And what we will prove is like alternating series, ratios test, root test, integral test, absolute convergence test, and then 2 more tests. Abel's test and Dirichlet test is new, are new. Okay, those 2 are new. Yeah. And then we will quickly finish up this chapter, and then we'll spend last period of time in a sequence of functions. Okay, that one need a bit of special treatment. It's quite new concept, actually. Okay, so far any question? Any problem with the plan? Okay, so bear in mind we are finishing this course. Yeah, we are finishing this course. So yeah, we are finishing this course. So yeah. Okay, so this is a road to finish MA1. Okay, road to finish MA1. So if there's no any problem, if you maybe I don't have time to go through your draft. Maybe yes, maybe no. But tonight, good luck. Tonight, come earlier to prepare, and then upload your draft, not draft, the PPT into the present folder so that we can directly use from my computer to present later. Sorry? The project, what draft? Select draft. No deadline, but just depend on whether I still have time to see through. Maybe I don't have time to see through already. Just present, it's okay, never mind one. I don't ask for a perfect presentation. What I ask for is how deal with a problem you met during presentation. Okay, that's the point I want to check on it. Okay, I won't expect a perfect presentation. In fact, there's no perfect presentation in this world. Okay, so even like the presentation I show you on the NVIDIA boss, you think it's perfect or not? Maybe you think it's quite perfect. Actually, there's some imperfection there as well. And then how he come across, how will he deal with this imperfection? It's because every time when he present, there's some flaw, and then he try to change it again. Why I say that his presentation might not be perfect? Because maybe one of them asked him, will AI control us one day? Actually, he did not address that question during the presentation. He direct away. Is there no need to care about whether AI can control us or not? For now, we're just focusing on creating the better chips. So this is how he deal with a problem that he cannot answer. He know how to direct people away. So this is what I want you to learn how to 随机应变 can you say? Okay, how to flexibility. Okay, 怎么随机应变 不是讲你去骗人呐、但是就是说，这是一个技巧啊，不是叫你去骗人的，不要用技巧去骗人。OK，yeah，but 真的回答不出来嘛？AI 会 control 我们吗？我不知道，对不对？but 如果不知道的情况下，你怎么去引导其他人？Understand 吗？Okay, this is what I want to see. It's not I want to see a perfect PPT or perfect English not like that. Okay, it's how you speak, how you convince people. That's what I want to see. So yeah, if you want to send me draft, you can. If I got time, I can look through. If not, then that's it. Okay, you just go. Okay. And regarding the project, later I will outline a deadline for you. Okay, and then I will make a cover sheet for you later so that you can submit it and also turn it in open for you and then you can submit there, check your similarity. Okay. And then after this project one is the project two. Actually, you can start now already. So what's about project two? You no need to write a formal report. What you need to do is you just make a summary on the last chapter. I will give you the chapter that you can refer in the book. So what I want you to do is like revision actually. Okay, I want you to do revision. So what you do is you summarize what you study inside the chapter of the book. Okay, and then I want you to maybe create some possible exam question, or you just search for some question that's related, and then you try and solve it yourself. Okay, that's project two. Project two is not really formal. It's about mainly about your revision on the last chapter. I want you to write a summary of it, and then maybe create some problem sheet for yourself. Maybe 1-2 questions like that. We will talk more afterwards. So just see you tonight first. Okay, 7 p.m. Please come earlier to prepare. I don't want to have any accident. Okay. All right. See you.